So let's begin. We are gonna be talking of homogeneous equations. So homogeneous equations. So the homogeneous equations here they're different from those in section 2.5. In 2.5, they were most certainly focused on their degrees and whatsoever not. Here, what we are gonna be doing is they're like suppose we have in general an of x. This is a constant, or rather, it can be a coefficient that is I don't know, depending on the independent variable. In this case, our independent variable is x. Then you have dn y divided by dxn. So the nth derivative, then plus. So we're going down. Like if this is the nth derivative, then we go to n minus 1. So in simple terms, this maybe if it was second derivative, then the next one is going to be the first derivative. That is why I'm saying we're going down. So it's here it's an minus 1 of x, then plus d n minus 1 y divided by dx n minus 1, then plus whatever that is going to be in between. Then we go to a 1 of x, then dy by dx. The reason I just put dy by dx there, you see that n now it's 1, right? So there is just 1 and 1. So this is just basically the first derivative. So this is then plus a 0. If we say n minus 1, we have 1 minus 1 will just yield a of 0 of x, then y. Then this is equal to 0. So when it is equal to 0 like that, this is um, the form of a differential equation that we consider to be a homogeneous. So this is what we call a homogeneous um, differential equation. Homogeneous nth differential equation, because here, I mean, in this case, we didn't specify the order. It's just the nth order in general. So it's a homogeneous nth order differential equation. So now one might ask that, so if you are saying this is the case, then I mean, if you're not writing it in general, how will it look like? Like in a way that they would normally give you guys. Maybe they say maybe they gave you 2y double prime plus xy equals 0. Okay, so the whole idea is that always it is going to be equal to 0. That is how you know that you are having a homogeneous differential equation. In this case, this one that we are having here, it's going to be called what? It's a second order. The second order, how do I know that? Because of the highest degree of our derivative is 2. So it's second order homogeneous differential equation, just like that. So that is the whole idea of a homogeneous differential equation. Now we are not yet interested in solving them as of yet, but then rather just introducing what is going on. Okay, so yeah, but then now one might ask also that what if instead, for example, they gave you something like 2 y double prime, maybe not use 2 y double prime. People start thinking it always has to be 2. Maybe they gave you y prime x squared minus 1 times y equals to e to the x. So what do you all think? Are we still going to consider this a homogeneous differential equation? Remember what I said. I said there, this is the standard form of a homogeneous differential equation. It has to equal to 0. So in this case, it is equal to a function that it's e to the x. So because of that reason, this one is no longer a homogeneous equation. So if it is not a homogeneous equation, then we say it is a non-homogeneous equation. It's a non-homogeneous equation. Okay. So basically, what this means is that in standard form, if you want to write the non-homogeneous equation, we can say for non-homogeneous equations, what we are having is that we have an of x dny dx to the n plus an minus 1 dn minus 1 of y, then d x to the n minus 1, then plus whatever functions that are in between there, then to a 1 of x dy by dx plus a naught y should be equal to g of x. G of x, it can be any function, but then now notice that our g of x in this case cannot be 0, because if g of x is 0, then it implies it will be a homogeneous. So yeah, where g of x is not 0, then that is considered non-homogeneous. So now to recap what we just said, a homogeneous differential equation, it always has to be equal to 0, like we said there in that standard form. That is why now on this example, we have proved that this one is a homogeneous equation. And then now if it is equal to some function there, according to this standard form, it tells us that it is a non-homogeneous equation. So like I said, we are not yet interested in solving them. I'm just, introducing to you guys what is basically going on, okay? So far, do we understand each other, like the difference between the two? Okay, that's great. So now let's move on and think of few things. I mean, after all, we will at the end of the day solve them. But then now let's sorry. Let's suppose now we have a homogeneous equation that possesses more than one solution. Okay. So if it possesses more than one solution, then there is a principle that is called superposition principle. It says that if y1 of x, y2 of x, going on like that to yn of x, are solutions of a homogeneous homogeneous um, differential equation, then they can be written as a linear combination of they can be written as a linear combination y equals c1 y1 of x plus c2 y2 of x plus then to the last one that will possibly be there. Here, let me do this, plus cn yn of x. Okay, so they're just written as a linear combination. All of them are solutions of a differential equation. So you therefore can write your solution as one thing. Y is equal to C1 YY. Y C1, C2 to Cn. They are just constant multiples of this you know, solutions that we are having. So if this doesn't make sense, you will see what I'm basically talking about when we start to do examples. But then just keep this in mind. This is the whole idea of if a homogeneous equation possesses more than one solution. Okay. And the other thing that you have to know is that a homogeneous equation, we have to know that a homogeneous equation, it always possess a trivial solution. It always possesses a trivial solution y equals 0. Okay, so y equals to 0, it's always a solution to I don't know, the differential homogeneous equation. So one might ask, what does this basically imply? For example, let's say I don't know, maybe we have y double prime plus 2xy equals 0. So this is a homogeneous differential equation. Why do I say that? Do we agree this is a homogeneous differential equation? Why? Yes, because our differential equation is equal to zero. So we know it's homogeneous, but then they tell us that it always possesses a trivial solution y equals zero. So the thing that we are going to try to do here is to verify that y equals zero is indeed the solution to that. So how do we verify? Verification of solution doesn't change. We will take this and say we want y derivative. The y derivative y prime of zero is just zero. Then also y double prime will just be zero. Then we go plug from left hand side of this differential equation. We had y double prime plus 2xy, then this will just be equal to y double prime is 0, then plus 2x, then y is also 0. So this is equal to 0, which is equal to the right hand side. So this is true. So that implies the statement there is true, that a homogeneous equation always possesses a trivial solution y equals 0. So yeah, I don't know. Maybe they can ask this in terms of theory or something like that. Don't get surprised that like maybe find the trivial or mention or maybe give the trivial solution for a homogeneous equation. When you start thinking it's a new way. So now you know that it always possesses a solution y equals 0. Okay. So yeah, like I said, we are not really yet in the idea of solving the homogeneous equation, but I feel that you guys must know this. So yeah, that is the whole idea. Can I continue, or maybe you all have a question up to so far? Hello, I can't hear you. You say what? I should go up where? Here at the beginning. Yes. Can you speak? Oh, okay. I thought that maybe you had a question, but then yeah. Now, since we know a few things now, we can move on to the idea of our solutions being linearly dependent or linearly independent. So now I'm going to introduce the idea of linear dependence and linear independence. So here, what I'm basically doing now, I'm summarizing 4.1. So, um, yeah, don't get confused as if why are we just moving on and on like that without you guys seeing where we are actually going with this. You will start to see where we are going with this when we do example. All the information that I'm giving you guys, it has to be sufficient until we start doing examples. So once we start doing examples to answer questions that will come on 4.1, that is when you will see the importance of all the things that I was telling you. So yeah, now if we are talking of linear dependence and linear independence, we are going to use what we call um, um, Wronskian determinant. But before that, maybe we can try to differentiate between the two. What is something that is linear dependent and something that is linear independent? Okay, so um, in theory, they say that functions f1 of x, f2 of x, da, 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 to fn of x are linearly dependent. depend- if they can be written as a linear combination of can be written as linear combination of the other. I got the wrong spelling. Linear combination of the other. So that is to say, let's suppose you have your f of x1 equals root x. Then you have your f of x2 maybe equals I don't know, x minus 1. Then um, maybe a f of x3 equals 5x minus root x, like that. But, yeah, if we have something like this, let me see which one can be written as a linear combination of the others. 5. So let me say here we have plus 5 instead. Then we can say um, f3 of x can be written as minus f1 of x minus f1 of x. So if we take minus of that, we want that part, then plus 5, then plus 5f2 of x. So if you multiply this one by 5, we will have 5x. Then, okay, let me see. So I have minus of my f1 is root x plus 5, then plus 5, my f of 2 is x minus 1. Yeah, then that is to say we're gonna have minus root x minus 5 from this part, then plus 5x. Maybe we should make this one a plus. So yeah, it can make sense. Then plus 5. So notice that this one and that one will go away. Then basically we have 5x minus root x. So which is just f of 3x. So you see that this is what they mean to say that let me go back there. If we are having function f of x1, then we are talking of linear dependent. Then a function that can be written as linear combination of others. So for example, we had this and that one, and we realized that f of x3 can be written as linear combination of these other two functions, like that. Okay, so that is the whole idea to say functions are linear dependent. So if you are able to write a function as a linear combination of the other two functions, then those functions are linear dependent. Otherwise, if you cannot do that, then they're obviously linearly independent. Okay, but the whole idea here will come more when we do something that we call a Wronskian determinant. That is something that is most important. But also, this is just the theory of linear dependent and linear independent functions, or maybe solutions of our differential equations. So, do we understand what I meant by this statement now from this example? Yeah. So that is the whole idea. Then now, let me just not waste time on this thing of linear what combination stuff and introduce what is going to be used most in this section. There is something called a Wronskian determinant. So when you start hearing determinant, you have to remember 1644. So a Wronskian determinant, it is the determinant where we are going to be able to classify easily the difference between linear dependent and linear independent functions. Okay, so it will help us classify difference from linear dependent functions, dependent functions, or maybe solutions and linear independent uh, functions. Okay, so um, here is what we will deduce. Let's say we let f1 of x, f2 of x, up to fn of x, let it possess at least n minus 1, let it possess at least n minus 1 derivatives, then the Wronskian, we will denote it by W. So let me just put there. I forgot to let you guys know that we're going to denote it by W. So this is how we are going to denote the Wronskian determinant with W. Then we are going to have the Wronskian of these functions that are there, f1 up to, we have nth functions. So we're going to say Wronskian of nth function that we are having, f1, f2, x is equal to um, you put the first function, f1 of x, on the first entry, then you put the second function there, then going on, depending on how many they gave you. But in general, now we have n of them. So just put whole there, like that. Then f of n of x, like that. You can do better than that. Yeah, much better. So we put them like that. On the first row, like that. Then this first column going down is going to contain f of 1 and its derivatives. And also this one will contain f of 2 and its derivatives, and this one will contain f of n and its derivative going down like that. Okay, so we said, let's go to the statement again. I'm going to highlight the most important part. We say these functions, they possess at least n minus 1 derivative. They possess at least that. So this is the important thing that you have to keep in mind. They possess at least n minus 1 derivative. So that is to say we are going to derive. So as we are going down the columns, we are going to be deriving this function until n minus 1 derivative. Okay. So that is to say if let's say for example you had y double prime plus 2y, and they tell you that something is its solution, maybe y to the y e to the x. Okay, then now you are going to say, since in this case we know that this is just d um, y square divided by d square x. Our n is 2. So if we are deriving at least n minus 1 derivatives, that means in this case you are having 2 minus 1. So we are going to derive one time. So this means that you are going to only derive once. So you are going to say y um, instead, let me just put it like this. We're going to say e to the x, then maybe let me use it as e to the 2x so you guys can see that I have derived. Then you derive it only once, so it's going to be 2e to the x. That is the whole idea. So how you know where you have to stop, it will be determined by the differential equation that they gave you there. Okay, yeah, in this case this is not even an equation. Maybe if I do it like this, then it's a homogeneous differential equation. So the highest order will tell you when to stop. If it's second derivative, that means you only derive once on your Wronskian when you put in the column there. I will put what is supposed to be there so long. I just want you guys to, like me, not get lost as I'm explaining the general format. So once you understand that, even remembering the thing will be easy. So if you have y triple prime, that means you will only going to put a function, derive it once, then derive it the second time. Because your n is 3, then you know that you have to stop at least n minus 1. So if n is 3, then it's 2 minus 1. I mean 3 minus 1, which is equal to 2. You are only going to do it twice. Okay, so that is the whole idea. Now let's write the general form and stop with this explanation thing. So let's see. We are going to derive f of 1. You derive it. I put prime there to show it's derived. Then you derive it the second time. Come on. That will make the matter. Oh, it's back. Yeah, I needed some space to construct this line now. Then you will keep doing that up to at least n minus 1 derivative. So you are going to do it up to at least n minus 1 derivative of 1 of x. So you do the same for this one. You derive it once. Then on the second row, on the third row, you're going to derive it uh, second derivative. Then you keep doing that up to there. Yeah. Similarly, you're gonna do the same thing if they gave you maybe, I don't know, up to them how many functions. They can give you three, four, but yeah, that is the whole idea. You derive that and take the second derivative of the last function, then goes on like that as well up to f of n to the at least n minus 1 derivative of x. So that is the general form of a Wronskian determinant. Ne? I know it might not make a lot of sense now, but just know the format and structure. You put the first function, then you take its derivative going down like that. How you will know when to stop, you look at the order of the given homogeneous differential equation. If it's second order, like here, your n is 2, then you know it has to possess at least n minus 1 derivative. So if it's 2, you plug 2 minus 1. So that is the whole idea. So you guys will see when we start doing an example. I still need to put, what is this? Some few notes regarding the Wronskian determinants. But so far, are we together? Yeah, that's great. I don't want to be speaking Chinese here and like people are not with me anymore. So let's move on and find out how is the Wronskian determinant going to help us. So let's suppose we have solutions let y1 of x. I mean, the notion can be different. It doesn't have to bother you. They can denote as y1 or f of 1. Just for as long as you know what you are doing, you know what you are doing. You don't have to get confused when. So the baseline is that do not cram. Okay, just know what you are dealing with. They can give you y1 as the solution. So let's say y1, y2 of x up to y of x are solutions to homogeneous differential equation. I'm just going to denote it as HDE. Yeah, I don't want to waste time writing the thing over and over again. So here is the first thing that you have to know. I'm still on linearity and linear dependence and linear independence. So if the Wronskian determinant of y1, y2 up to I don't know how many solutions can be there, but in general, let's say the nth solution, then you find that Wronskian determinant to not be equal to 0. And you find that Wronskian determinant to not be equal to 0. What does it imply? It implies that you are having solutions that are linear independent. Okay? Then if the Wronskian determinant, of y1, our solutions, y2 of x up to yn of x is equal to 0, what will that mean? Anyone willing to try? Then they are going to be linear dependent. Yes, that is correct. They are linear dependent. Okay, so that is the whole idea. So keep this in mind. If you they give you a set of solution and they ask you, are those solution linear dependent or linear independent? You just have to compute their Wronskian determinant. And if that determinant is not equal to zero, then it implies they are linear independent. And if the Wronskian determinant is zero, it implies they are linear dependent. Okay? So that is the idea. This is important. You go in there not knowing this, or you go to write a test or whatever without knowing this off by heart, you're not gonna win. Because this follows up, what follows up after this, especially this first one, what follows up is what we call fundamental fundamental set of solution. So why I'm saying this is important, it implies that if you have a set of solution that is linear independent, so this is our set of solution. If we compute the Wronskian determinant and find them to be not equal zero, it implies they are linearly independent. So by fundamental set of solution, we say that if your set of solutions y1, y2 of x up to yn of x are linearly independent, uh, then they are called fundamental set of solution. Okay, so if you find the Wronskian of this to not be zero, it will imply they are linearly independent, and also those set of solution, they are therefore what we call a fundamental set of solutions. And if you are having fundamental set of solutions, those solutions, you can therefore call them general solutions to your differential equation. So this is the last point. General solution. So general solution is of the form what did I say at the beginning? I told you guys that it has to be y equals to c1, y1 of x plus c2, y2 of x plus dash 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 up to the last one. In this case, we are dealing with the n solutions. So y of n x. So this is the form that you're going to write a general solution. But y1, y2, and y of n up to y of n will only be general solution. They will only be general solution if they are fundamental set of solution. In simple terms, that is to say, if you find the Wronskian not to be zero, because something to be a fundamental set, it has to be linear independent, and something that is linear independent, it implies its Wronskian is not zero. So yeah, that is the whole idea. You wrote everything that I'm saying in this class now. You go and I don't know, wherever you are studying, you summarize it nicely in accordance to the way you understand, and you put it on your wall. You look at it there every time you are practicing questions related to these sections. You will never go wrong. So that is all about 4.1. As far as I know, this is all about 4.1. If there is something that I didn't state there, I I don't know. But as far as I know, this has to be all about the things. So can we start doing examples so you guys can see where I'm going with all this. I mean, this is just a whole of writing, a lot of words and stuff like that. Let's see how we can use these words to our advantage to be able to, answer the questions. Maybe they can say, um, verify the given, verify that the given functions form, the given function form a fundamental set of solutions. Then, if they do, then find general form, general form or general solution. I mean, it's just interchanging of words. Okay, let's say for the first one, they give you y double prime plus y prime minus 12y equals 0. So this question I abducted it from the textbook. So yeah, you can it's question the first question on the exercise. Then they gave you the solutions or rather functions as e to the minus 3x and e to the 4x on the interval minus infinity to infinity. So what are we asked to do? We are asked to verify if this a fundamental set of solution. Then if they are, then we should I don't know, write the general form. So in order for us to do that, we have to first compute the Wronskian determinant. So I can say this is y1 and this is y2. So y1 equals y1 of x equals to the minus 3x. Then y2 of x equals to the 4x. So to do a Wronskian determinant for that, what are we going to say? Wronskian of y1 of x, Wronskian determinant y2 of x will be given by um, y1 of x, then y2 of x. So where there is y1 of x in that column, I have to start taking their derivative. Then when am I gonna stop deriving these functions? Like I said, you go and check the given homogeneous differential equation. You look at the highest order. In this case, it is a homogeneous equation of second order. So if it's second order, it implies that n equals 2. And we know, according to the Wronskian determinant, they have to possess at least n minus 1 derivatives. So in this case, the number of times that we're going to derive is basically 2 minus 1, which is 1. So we are only going to derive once. So we are going to derive one time here. So we are going to just say y1 prime and y2 prime. Are you all understanding? Okay. Then now let's start putting functions there. What is y1? My y1 is e raised to minus 3x. My y2 is e raised to 4x. So according to this, I have to take the derivative. I'm going to get minus 3 e to the minus 3x. That is the derivative of, this function. And the derivative of this one is 4e to the 4x. Just like that. Then now, yeah, let's see if people remember how to find the determinant. Remember, if you have a 2 by 2, let's say A, B, C, D, the determinant of this is just AB minus BC. Okay. If you don't recall how to find determinants, I think, yeah, I did videos about they are there, or you can, go revise anywhere you like. But yeah, on my channel, they are also there. How to find determinant of 2 by 2, 3 by 3. Like you saw in general, Wronskian, they can give you as many functions as they like. But at most, they will give 3. Yeah. Then how do we go about this? Then it implies that this is equal to, according to what I wrote there, just to remind people, we're going to have 4 e to the minus 3x times e to the 4x. My a is this one, my b is that one. So I multiply them, then I subtract minus 3 e to the 4x times e to the minus 3x. Just like that. Okay, my b is e to the 4x, which is that one. Then my c is minus 3e to the minus 3x. So this is how it comes out. Then we can therefore say this is basically equal to 4. Bases are the same, so it's just going to be 4e to the x. Then subtract becomes plus because of that. Then we minus 3e to the x. So this is basically 7e to the x. So what can we say about this now? Notice that this function, for all values of x, it will never be 0. There is no a value of x that you can plug there to make e to the x will never be equal to 0. So if e to the x will never be equal to 0, it implies 7 e to the x will also not be equal to 0. Okay, but then, I mean, um, yeah, let's see. I think there was additional information. The additional information is this: they give you an interval. X is between negative infinity to infinity. So you can choose any value of x. If you choose x to be 0, you are going to get your determinant as 7. Then this is obviously not equal to 0. Then we know that if our Wronskian determinant is not equal to 0, what do we say? So we see that w of y1 of x, y2 of x is equal to 7 e to the x, which cannot be equal to 0. This implies our function, our solution are linear independent. Linear independent. Yeah. Then, if they are linear independent, what does it imply? Therefore, it implies y1 of x, which is equal to e to the minus 3x, and y2 of x, which is equal to e to the 4x, form they form a fundamental set of solution. So we know that if they form a fundamental set of solution, then therefore it implies we can find the general form, or rather the general solution. So we know that the general solution is given by y equals to c1 y1 of x plus c2 y2 of x. So it implies we have y c1 e to the minus 3x, then plus c2 e to the 4x. We are done. That is the answer to that question. Are we together? You got lost where? When we're doing the Wronskian here, where this part where we are starting to derive. Yes, you can ask your question, Goki. You were saying where? Okay, but now I'm curious. What was your question? Oh, okay, okay, that's cool. But yeah, this is the format that you guys are gonna answer such questions. If they ask you to verify, or they can just instead of giving you guys all this part, they can just say find the general form or find the general solution. So if they just say this, it's a trick. You don't just go and say according to the standard form of general solution, then you say y1 c1 e to the minus 3x plus c2 e to the 4x. You don't do that. You have to first determine the Wronskian and verify whether is it going to be linear dependent or linear independent. Because from what I told you about general solution, this will only be general solution if the fundamental sets are if those functions form a fundamental set of solution or the Wronskian is not equal to zero. So you cannot say those functions they possess a general solution if their Wronskian determinant is equal to zero. So if they just ask this alone, don't go and write that without verifying that indeed they are linearly independent. Okay? So let's do the next question. Let's say now they gave you something like x squared y double prime plus x y prime plus y equals 0. Then they gave you y1 equals cos of Linux. They gave you y2 as sine of Linux on the interval 0 to positive infinity. Okay, so this is where the things will be defined. And the question is find the general form or verify. Still the same question. So the first thing that we do, what do? We found out first the Wronskian of y1 of x and y2. So we are going to say what is our y1? Hello? You are you guys seeing the screen? Who is there anyone who's not seeing the screen? Oh, that's great. I thought that maybe there is someone who's not seeing the things. So yeah. So how do we find the Wronskian? We're gonna say y1, y2. Let me just do this. Gonna say y1 of x, then y2 of x. Then what do I, how many times are we going to derive this? We are going to derive it what? Once. Yeah, that's great. How do you know that? You use your homogeneous differential equation. You look at the highest order is second order, then that implies n is equal to 2. Then we know the atries have to possess n minus 1 derivatives. So that implies we're going to have 2 minus 1, which is 1. Then we know we only have to derive once. Okay? Then that implies we're going to have y1 prime of, then y2 prime of x. Just like that. Then let's go on and plug in the functions. We have cos ln of x, sine um, ln of x. What is the derivation of cos ln of x? This is composition of functions, isn't it? What is the derivation of this, guys? d by, dx of cos composed of limits. We say it's equal to what? Negative sine ln of x. This is the answer, over x. Okay? So, yeah, you have to remember everything, like I said, for this module. Remember that if we have, we want to find the derivative of f composed g, f composed g of x. I don't know if this is the right format of writing the composition. But yeah, it has to be something like that. F composed g of x. Yeah, I think this is the right way. Then that is the derivative of f. You derive f, you don't do anything to g, then you multiply that with the derivative of g. So in this case, our g of x is ln x. So that is where over x is coming from, because derivative of ln x is 1 over x. Then we are multiplying with it, then it's something like that. Thank you so much. That is correct. I agree. Then we say we have minus sine ln of x divided by x. Then what about of this one? It's just going to be cos ln of x over x. So now we can start doing the things on the thing. This times that, just going to be cos ln of x square divided by x. So this must subtract. Since there is a negative there, I think it will therefore become positive. So we say plus sine ln of x all square divided by x. Okay, so since they gave us an interval there, you don't have to then say actually I can do this. I can write this as cos square ln of x plus sine square ln of x divided by x. I mean, the denominator is the same. I'm allowed to write this. So this is showing you what? What is this? This the numerator is just equal to 1. Hello? You say what? Yeah, so this we can just see sine cos of that plus sine of, you know, we can just say it's 1 over x. Therefore, this is our, what is it? Our Wronskian determinant. So our Wronskian determinant, we were given an interval that says x is between 0 to infinity, where 0 is not included, it's a round bracket. So everything that is positive. So you can choose, I don't know, any value of x. You see that this will never be equal to 0. If you choose x as 1, you'll get 1. 1 is not equal to 0, whichever value you're going to choose. Okay, so that is not equal to 0. What does it imply if our Wronskian is not equal to 0? Therefore, Wronskian of y1 of x, y2 of x equals 1 all over x, which we know is not equal to 0. It implies we are having linear independent solutions. So y1 and y2 are linear independent solutions. So if they are linearly independent, therefore they form fundamental set of solutions. So we can say our general solution is y c1 cos limx plus c2 sine limx, just like that. So far, so good. Yes. You say if what? We change the interval to be negative infinity to infinity. If they included infinity, I mean, we are going to be dividing by a very big number. I mean, that will only approach zero if we are talking of limits. But infinity is basically not a number, so we cannot really deduce yeah, what that was going to be. But otherwise, this is the whole idea of 4.1. This is what is happening. Let me try and see if I can find questions maybe in the previous exam paper that required Wronskian determinant being even. Um, Nine here that are not being they are already deep in context, so we can find one from the previous exam. Let me check previous semester test. Um, last year semester test one was ending on chapter two, and I don't think I have semester test two in this device. So I'll just copy more questions from the textbook. But it's easy stuff, ne? Hmm? Do you guys not agree it's easy stuff, can? Or are you shaking, good people? Hmm? For now. Yeah, I mean, what does that have to imply in the future? It might be not giving anymore. Mhm. I want us to do something that is a 3 by 3, but we didn't put 3 by 3 here. I don't know what is the idea. We can actually formulate our own. Yeah, why not do that? Let me give you guys one from my head. Let's say they gave you x, y triple prime plus y equals 0, where you have y1 of x equals lim um, ln of x squared y2 in ln of x to the power 3 um, plus x, and y3, it's maybe let me just say x squared. Yeah, or just x. So we have something like that. Ne? I'm just giving this one so you guys don't think it's always gonna be a 2 by 2. So you have to remember also how to find the determinant of a 3 by 3. So let's do that quickly. We have y1, Wronskian of y1, y2, y3 will be we're gonna have y1, y2, y3. Then how many times are we going to derive? How many? Eh? Twice. Yes. We are going to derive twice. We look at this. The highest order is 3. So it's n minus 1. Where our n is 3, then it's 3 minus 1, which is 2. That is how we know we derive twice. Okay? Then we want derivative of y1 and second derivative of y1. And also first derivative of y1 and second derivative of y2. I mean y2. Then first derivative of y3 and second derivative of y3. Yeah. Then what do we have? Our y1 is ln x squared. Our y2 is ln um actually y2, okay, I wrote it like that for a purpose. Let me do this. Can we not simplify y2 to what? It simplifies to what? It simplifies to x cubed e to the power x. Yeah. Then our y3 is just x. Phumelela, you here with us, Bafana. Are you alive there or things are kicking? You'll be fine, my brother. Don't worry. Then the derivative of ln x squared, what is it going to be? Okay. So it's like this. And one x will cancel there. Ne? So it's 2 all over x. Hmm? Yeah. Then what about this one? We're going to have 3 x squared e to the x plus x cubed e to the x. Then of this one is just going to be 1. So these are the type of questions they will put there. They won't put something that is just easy to go about. They want to see you. Then the derivative of 1 over x. So I'm basically dealing with 2 x to the negative 1. So what is the derivative of this? Minus 2x to the negative 2. So basically, I have minus 2 all over x squared, right? Then now the derivative of this one, we apply product rule twice. So it's gonna be 6x e to the x plus 3x squared e to the x. Then for this one, it's just gonna be this thing repeating itself. So I'm gonna write it below here. So it's gonna be plus 3x squared e to the x plus x to the third e to the x. Then the derivative of 1 is just going to be 0. Now we want to find the determinant of that. I can pick and choose whichever one that makes my life more easy, right? So when you find the determinant of a 3 by 3, just remember this: plus, minus, plus, minus, plus, minus, plus, minus, plus. So these signs, they go with the respective row and column. So in this, it implies the first entry is plus, the second one is like that, then this one is negative according to that, then the other one is plus, and so forth. This one is negative, this one is positive, this one is negative, and the middle one there is positive. Depending on which way you want to go, I'll utilize the opportunity of having a zero there. So I can use you know this one. So if I'm using this row, I have to pay attention to its signs as well. It's plus, minus, plus. So the importance of that is that like you don't make errors when you're doing um, the determinant thing. So if I'm using this, I'll start here. I have x. I cancel this row in that column. Then I have the determinant of 2 all over x, 3x squared e to the x plus x to the third e to the x. Then what else? Minus 2 all over x squared. Then let's see here, we can say 6x e to the x plus 1. Then these two are like terms, so I can also say plus 6x squared e to the x plus 3x squared e to the x plus x to the third e to the x. Can't do that. You're supposed to be just plus what do you call plus x to the third e to the x. Remember, I took these two as like terms. They are just there. So I rewrote it twice. That was the mistake. Then I'll close that smaller matrix for determining. When I come to this one, I cancel this row and this column. I remain with this, that, and that. Okay? But then the importance of sign, that is where it comes in. The sign here is negative for this one. I have to say minus 1 multiplied by ln x squared minus 2 all over x squared. Then the other one, x to the third e to the x. Then on the last entry, what am I gonna have? I'm gonna have 6x e to the x plus 6x squared e to the x plus x cubed e to the x. And I close that. Then the reason I chose 0, the last one was supposed to therefore be plus 0 times whatever thing. In this case, it was going to be this part. But then anything multiplied by 0 is 0. So I'm minimizing taking a lot of time there, trying to do a determinant. If you use this this first row. Notice you're gonna multiply with everything there. Nothing was gonna go away. But this zero is making something to go away. Hence, um, minimizing my work. So I'm gonna have this determinant is equal to x. Then now I say 2 over x. It should be multiplied with what? With 6x e to the x plus 6x squared e to the x plus x cubed e to the x. Then minus. So now since this is a 2 by 2, we do it the regular way. Minus. So this will just become a plus somehow because of that. This times that. So it's 2x squared multiplied with 3x squared e to the x plus x cubed e to the x. Then minus, I'm done with this part. So I'm here now. Minus of this times that, which is ln x squared multiplied with 6x e to the x plus 6x squared e to the x plus not e, but rather, what's that? X to the third e to the x. Then I close the bracket. I say minus, according to how we find the determinant of a 2 by 2. There's to minus this times that. But this also comes with a negative again. Then hey, it becomes a plus. Then I say 2 all over x squared, x to the third, e to the x. Just like that. So now we have x into this by that will just give us 12 e to x. Then this one by that will give us plus 12x e to the x, then plus x squared e to the x. Okay. Um, I don't know what else. Yeah, it was done like that. This part. We put this in bracket like that. Then plus this by that will just give us 6 e to the x. Then this times that will just give us 2x e to the x. Right? Mm, yeah. Then what do we say? Surely there is no need for this brackets, but it's fine. Then we say minus. Um, what do we have now? We multiply b in here. Okay. We have um, ln x squared. I can say 2, but that's fine. Ln x squared times 6x e to the x. Mm, then let me keep the bracket. Then plus ln. Is there any need for us to expand this one? Now I feel like this one we can leave it like this. Yeah, I'll show you guys what I mean. There is no need for it to get expanded. Okay, you say what? Here. Sure. Thank you. Then, yeah, for this one, I'm saying, um, let's not expand it. Then here, we will leave that one as it is, lim x squared times 6x e to the x plus 6x squared e to the x. Um, Plus x to the third e to the x. Then plus, now I'm here, this times that will just give us 2e to the x. Alright. So what can we say? Let's see and stop wasting time trying to simplify. Let's see the interval. In which interval can we give this to be, defined? For this function, it's all values of x greater than 0. Strictly, I mean, for this one, it takes all elements. So for this one, it's an element from negative infinity to infinity. It takes everything. But then this one, this one, it is 3. So this one wants to take at 0 everything greater than 0 going there. Then for x also takes negative infinity to infinity. So where you see that those three functions, their domain intersects at 0 to infinity. So we can say 0 to infinity. It's our interval. So you can choose any number between 0 and infinity and see what is going to happen. I think it is, but the lim doesn't take 0. So let's choose 1. So if we choose x to be 1, we're going to have let x equals 1 because it's in that interval. We're going to find the Wronskian determinant as we plug 1 there, it's just going to be 1. We plug 1 there, we get 12e. We plug 1 there, we get again plus 12e. We plug 1 there, we're going to get plus 2e. Okay, then what is it? Do I still need to keep these brackets now? I don't need, there is no need for the bracket anymore. Then plus I plug 1 in here. I'm gonna get 6e. Then I plug 1 there, I'm gonna get plus 2e. Then minus. What is ln of 1? Ln of 1? 0. So that implies this whole 1 is just going to become 0. So we don't do anything. So this negative was affecting everything there. So e to the 1 is just going to be minus 2e. So this one and that one cancels. So you see that the Wronskian is going to be, I don't know, 12 plus 12, 24 plus 6, 30. Then we have 32e. 32e, which is not equal to 0. You see how you can use your interval. If we have something that is looking complicated like this one. We just choose x. That is in this domain. For these three functions, their domain intersect at 0 and infinity. Hope you guys remember how to find domain of three functions and combine it to be one, where they are all defined. These three functions, they are all defined at 0 to infinity. Okay, so you can choose a number that lies between 0 and infinity. We chose 1. So when we choose 1, our Wronskian simplifies to this. So to conclude, we can say, therefore, y equals. So since it's like this, we know it's linear, independent. So if it's linear independent, then it also implies that we can write the general solution. So C1, Y1, what is Y1? I don't recall. It's been a while. Ln x square, then plus C2, what is Y2? I think it was x to the third, e to the x, then plus C3 x. So that will be a general solution. But we can't just plug the functions into the standard form of general solution and say, yes, these are general solutions without us proving this first. We have to first show that the Wronskian is not zero. If the Wronskian was zero, then it will not have a general solution where we write it like this. Any questions? Subtraction. If there are no questions, I'll just leave you guys with the technique of 4.2, which is called reduction of order. Let me just quickly put it down here. Or is it? There we go. We have 1, 2, times 5, to the minus. So far, we understand the idea of Wronskian determinant, linear independence, linear dependence, how to answer a question of general solution. If there's ne, okay. So in our next session, we will do 4.2. 4.2 is what they call reduction of order. Don't worry, today we're not gonna do questions based off on this. I just want to leave you guys with the idea of what is going to happen on 4.2. So you saw how in previous section they gave us both solutions and we just had to verify whether they give general solution and whatsoever not. What if now they give us a differential equation? Um, let's say x squared divided by dx plus xy equals 1 or equals x to the third. Then they give us a solution y1. Maybe, for example, they say that solution is uh, x squared, and they want you to find y2. This differential equation, they tell you it doesn't possess only one solution. It possesses more than that, and they want the second solution y2. So they want y2 of x. How are you gonna do that? This is where the technique of reduction of order kicks in. I will introduce it nicely on tomorrow's session where I give you guys everything. But today I will leave you all um, with the equation that you have to know. The equation, it says y2 of x is equal to y1 of x multiplied by the integral of e to the power minus integral of p of x dx divided by y1 squared. Y1 squared. So y1 of x squared dx. This has to be your best friend when you are dealing with a technique called reduction of order. They give you one solution and they want you to find the first one. I mean the second one. So before you apply this equation, what will you have to first do? You will have to first verify that this is indeed the solution to your given differential equation. Okay, after you verify that, you then put your differential equation in standard form. Why do we put it in standard form? So we can find our p of x there. Realize there is integral of p of x there. So we need p of x. If it's just like this and we go and pick x as our p of x, we will get it wrong. So we need to put it in standard form as well. Then everything else will follow. You just use this equation, plug in everything, then simplify, integrate, then find what is our second solution. Okay, so tomorrow we are on this type of technique. So yeah, make sure you go and memorize this technique. If you feel like you have time to, go through the section as well, just do that. But then at the end of the day, it will be for your own benefit. Yet tomorrow we are still going to introduce this. Like we always do, I'll give notes on reduction of order, so you guys can know what to do. Then we'll start doing questions. Okay? Yeah. So thank you so much, guys. We have reached the end of our session.